In the last lecture, we had discussed the concept of stress. We had defined stress as the ratio of the load or the force applied over the area which is resisting the force. Before we go ahead and discuss anything further, let us solve a few problems to understand the concept better. The first question is like this. We have a bar which is made in two portions. This area of cross section is A and this area of cross section is 2A, and the force applied is P. Now we have to find out the stress in the bar at this location and this location. Let's say this is section 1 and this is section 2. So the stress at section 1 is equal to P upon A, and the stress at section 2 is equal to P upon twice A. Now let's say that the length is L and this length is also L, and let's say this point is called point R or point S. Now if we have to figure out the deflection of point S, we cannot do that now directly because we haven't still figured out the relation between strain and stress. So we have also seen what strain is. Strain is equal to the change in length over original length of any object. Now if we take the stress and strain and if we see them closely, then stress is totally independent of the material. Similarly, strain is the stress strain is delta L upon L. This is also independent of the material. Now if we see the two things closely, then even the two things seem to be independent of each other, which means the strain is independent of stress. Is that so? We need to ask the question, are they independent? Which means, can we arbitrarily assign both stress and strain at a given point in any material? That is not correct. We cannot do that. There is a relationship between stress and strain. So it has been found that stress is proportional to strain, and this relationship is valid for a lot of materials. If we remove the proportionality and put this relationship in form of an equation, stress can be written as a constant multiplied by strain. Then this constant is known as the modulus of elasticity or Young's modulus. It is normally denoted by E. It is denoted by E. So the stress is equal to E multiplied by strain. Now it is a common practice to denote stress by sigma and strain by epsilon. So the relationship is sigma equal to E times epsilon. Now this is the relationship for normal stress. And E is a material constant. What is meant by material constant is that if we take a common material like steel or aluminum or concrete, E is a constant, which means that doesn't change for that material under normal circumstances. So E has to be provided as a number. Now, what is the unit of E? Now, if we see what is the unit of stress, sigma is force upon area. The unit of force is Newton and area unit is meter square. So the unit of stress is the same as the unit of pressure, which is nothing but pascals. Now there is another practice which is to define the area in millimeter square, in which case it becomes megapascals, but that is not required right now. Now let us see this unit of strain. Strain is change of length over original length. The unit of this will be meter over meter, which means dimensionless. So strain is dimensionless and stress has a unit of pressure, or let's say Pascal. So E, which is nothing but sigma over epsilon, will have the unit of stress then, which means that it will be having the unit of Pascal or pressure. This is about the unit of E. Now, the most commonly used material is steel. So if we take steel, the E value of steel is found to be around 210 gigapascals, or 210 multiplied by 10 to the power 9 pascals. That's a very high value. For aluminum, it is aluminum E is around 70 GPa, which is around 1/3 of steel's Young's modulus. Now let's solve the same problem which was solved some time back, which is this one. This problem. Let us solve this problem again and try to figure out what will be the deflection of point A. Over here we assume that the Young's modulus of the material is E, and other quantities are all provided here. Let's solve this problem. So the problem is like this. we have a split bar, each of which is L in length. Area of cross section is A. This area of cross section is 2A. This area is A, and the force applied is P. We have to find out this the deflection of point S. Now first we have to do what is known as the free body diagram of the two portions. Let's say that this point is T and this point is U here. So if we take section or portion UT, so we isolate the section UT. So this is section UT. The P force is acted directly as P, obviously because the force is P, so the reaction must be equal to P. So this is how its free body diagram looks like. Now, because the area is 2A, the stress in this is P upon 2A. E is given as E, which means that we assume that by Young's modulus is E. So the strain is sigma upon E. That is nothing but P upon 2AE. Now the length of this portion is L. So the change in its length, delta L, will be equal to, or let's say delta L of UT, it will be equal to the strain multiplied by L, because the strain is delta L upon L. So delta L of UT will be equal to epsilon multiplied by L, which is nothing but PL upon 2AE. Now this change in length is actually the displacement of this point T, because this portion is fixed, it cannot move, hence all the deflection will be occurring at T. So the point T moves like this by this much amount. So let's say if I draw it figuratively here, this is delta L of UT. Okay. Now let's take the other portion. The other portion is portion ST. Now ST, if we isolate ST, diagram can be drawn like this. The applied force is P. Obviously the reaction also has to be equal to P. Its length is equal to L and its area of cross section is A. Over here the stress will be equal to P upon A. This is stress. And again, because E is given, so the strain will be equal to stress upon E, which is nothing but P upon AE. Now the change in length of ST will be equal to its strain multiplied by its length, which is equal to PL upon AE. Now we can assume that this portion is fixed, which is that point T is fixed and point sorry, point T is fixed and point S has moved by this much distance. So we can draw the diagram like this. This point is fixed here. This is an assumption that the point T is fixed and point S moves by this much distance, which is delta L of ST. So point S moves by delta L ST with respect to point T. So the deflection of S with respect to T is equal to delta L ST, which is nothing but PL upon AE. But we have to also remember that point T itself is moving with respect to point U, or with respect to the fixity. This is the fixity. Now in this case, if we write the deflection of T with respect to U is equal to delta L of UT, which is nothing but PL upon twice AE. Hence, the total deflection of S is equal to the sum of these two deflections. It's delta L ST plus delta L UT, which is nothing but PL upon AE plus PL upon twice AE, which is nothing but PL upon AE taken as common 1 plus 1 upon 2, which is nothing but 3 by 2 PL upon AE. That is the deflection which point S has in this problem. So this was fairly mid-level difficult problem, I will say. It was not very easy at the time. At the same time, it was not very difficult also. But these are the kind of problems which you can expect to see in GATE or other competitive examinations. These problems test not only the knowledge, but also they test how fast you are able to disseminate the knowledge to a particular problem, and how fast are you able to disintegrate a large problem into many small problems which can be tackled independently. Now, if in the same problem, if I increase the number of individual parts of the bar, let's say I have a problem in which I have, let's say, 5 portions or 10 portions. Now it's very easy. Now you know how to solve it without much difficulty. Basically, it is nothing but you have to apply the same method, but that many number of times as the number of parts are there in the bar. So this, in a nutshell, is the gamut of main principles which are there in solid mechanics or strength of materials. So the 3 main things are the stress, the strain, and the constitutive law. Now, before we go ahead and tackle more difficult problems, let us also see how normal materials behave in real life. It's a very important thing in my opinion, because the behavior of material finally will govern how good the design is if you use that particular material in the design. Now let's see how steel behaves when it is loaded with a uniaxial force, which means that I have what is known as a simple specimen of steel. Let's say the specimen of steel is like this, and we have a force applied here, and this end is constrained. I assume that the length is L and the area of cross section is A. So obviously the stress which has been impounded on the material is P upon A, assuming that area of cross section is uniform throughout the length. So it is A here, it is A here, it is A here also, and it is A here also. Everywhere it is A. Such a specimen is known as prismatic. What is prismatic? Prismatic is that specimen or that object whose area is constant throughout the length. Now, because the stress is a constant now, because unless of course you increase the force, area is not changing, so the stress is a constant number, unless of course the force is changed. So if the force is constant, then the stress is constant. Now, if the force is increased, the stress obviously increases because P is increasing. So sigma being directly proportional to P, the stress also increases. So people have done a lot of experiments, and they have figured out that if we create a diagram I'm sorry, I'm just a bit bad in drawing. Now, if we take the stress along y-axis and the strain along x-axis, and we do this experiment, which is that the specimen is taken to a machine which is known as Universal Testing Machine, UTM, and there it is pulled with a force which is slowly increasing. So it has been seen experimentally that the strain increases proportionally as the stress increases, which is nothing but the constitutive equation, which is sigma is equal to E epsilon, which means as the stress increases, the strain also increases. So it has been seen that the stress and strain increase proportionally for some load. Till the load is some number, I will tell what that some number is, but till it is some number, they increase proportionally, which means that this portion of the diagram is a straight line. Now, obviously, we can see that if this is a straight line and this is stress and this strain, then this angle is theta, and that is nothing but tan inverse of E. We can figure out that because the tangent of this is the height divided by base. Height is stress, base is strain. So the tangent is height by base, which is nothing but sigma upon E, which is E. So the angle is tan inverse of E. Now we also know from practical considerations that E value for steel and aluminum is very high number. So the theta is very close to 90 degree because it's very high number. The E value is very high, and for 90 degree the tangent is infinity. So it's very close to 90. It is very whatever. I mean, in terms of uniform scale, it may be around 89 or 89.5 degrees or whatever it is. Now for some load, it increases till a particular point, and after that it droops. What is the meaning of drooping? It tries to go like that. It flattens out a bit, and then there is for a very small change in force, there's a very large increase in its strain, and then it again loads up slightly. But in this portion, it is not a line, it is a curve. And then finally, it has been seen that after a certain point, it droops like this, and then the specimen breaks here. Now, this is a very important curve to understand carefully. And let's see this point till which the curve is a straight line, this point. This is called proportional limit. Then the point till which, now it has again been experimentally seen that there is a point in the curve till which, if we remove the force, then the strain retracts completely, which means the specimen goes back to its original length. That point is called elastic limit. Now, it has also been seen that for steel, just after elastic limit, the length changes without any appreciable change in force. The point where it starts happening is called yield point. Now, I'm drawing the diagram here as very exaggerated fashion. In reality, the proportional limit, elastic limit, and yield point, they are all very close to each other. So for all practical considerations, I can just draw the diagram again. It will look like this. It is a straight line. Then this is the point at which proportional, elastic, and yield will be very close to each other. They will be almost there at the same point. Beyond that, beyond yield, the curve doesn't remain linear. It becomes some arbitrary curve. Now, obviously, this is sigma and epsilon. That curve is like, if we retract from this point, for example, then we will not be able to come back to the original dimension. It will drop down from there like this. This line is equal in slope to the elastic line. This portion is the permanent deformation in the material. This is called plastic set. Now, after that point, after which the curve drops, that point is called ultimate tensile strength. And beyond this, the material is highly unstable and it breaks here. This point is called failure strain. In design, normally we use ultimate tensile strength. That is a normal consideration. We do not go to failure strength because we do not know what happens in this zone. We have no idea. This is highly unstable zone. This is how the stress strain curve of steel looks like. And this is also the stress strain curve of aluminum and a lot of other metals. But normally steel and aluminum are the most widely used metals. So we have to remember the curve for them. There are various grades of steel, various alloys of steel, and they have different values of the yield point. This is the yield point, so I just put that as YP as the yield point, and the UTS, this is called UTS, and the failure strain. So the yield point and the UTS and the failure strain, they change from alloy to alloy. E value is almost equal for all the alloys. For most of our study in this subject, we will not be going beyond yield point. We will be working mostly in the elastic zone only, which means that if we remove the force, we retract the curve exactly, and as we take the force to zero, all the strain is recovered, which means the strain goes back to zero. Please remember the curve and various points which are there in this curve. In the next lecture, we will see how to solve some more complex problems and how to use this information which we have studied till now in solving problems of practical consideration.